Hello, I'm Samuel Adkins, and this is my presentation for CAP6640 at Florida Atlantic University. Today I'm going to be talking about multilingual language processing as it relates in the field of NLP in general. In this presentation, I'll do a short introduction. I am going to go over what multilingual NLP is, talk about some of the challenges in the field, current solutions to those challenges, and current natural language processing multilingual models, and then quickly cover some of the applications. A little bit about myself first. I'm a senior BSMS student. I am about to get my bachelor's in computer science, and I'm pursuing a master's in artificial intelligence. The reason I chose multilingual NLP is because I love different languages and cultures, and I've always dreamed of being able to talk to all the cultures and experience their side of the internet. Especially being a computer scientist person, I spend a lot of my time on the internet, and there's so much knowledge that is at our fingertips, but we cannot interact with because of a language barrier. Just to hone in on that point a little bit, the internet and humanity is being held back by the language barrier, especially in this time of technology, where we could talk to anyone. We can access knowledge immediately from anywhere now, but for most people, most knowledge is a language they cannot understand. Because we have such a multilingual world, it only makes sense that at some point we need to develop a multilingual natural language processing system. Multilingual language processing systems are computer programs that are developed to understand different languages as input. You can break up this problem into two main approaches: build a separate system for each language, or build a single system capable of handling multiple languages. Because most of the internet is written in English, most of the models have been made for English. This is because scientists are constantly trying to make the most accurate model. And to make the most accurate model, you need the biggest sample size. A lot of the other languages do not have a lot of text on the internet, and so they often get left out of the new advances in NLP. Fortunately, new techniques are being made to make better and more effective models that are in some areas just as effective as English models. Some of these techniques are cross-lingual transfer, where they fine-tune multilingual models on English training sets and evaluate it on each language's test set. There's also cross-lingual embedding, which we will see with Google's BERT. There's translate train, where machine translates the English training set to another language and fine-tunes a multi-language model on that. And translate train all, where the machine translates the training set to all languages and fine-tunes a multilingual model on that. Here we can see a quick overview of the application of some of those different techniques. On the right side, we can see a translation-based method that translates the input into English. Here you can see the training set is going from German to English, and the test set is going from French to English. And then the model performs the text processing. What seems to be more popular these days is on the left, joint multilingual learning trains, that it trains on a single node with a mixed data set in all languages to enable data and parameter sharing wherever applicable. Both these models are still used, and they both have pros and cons. Before I get into more of the solutions to creating multilingual models, especially for low resource languages, let's talk about some of the multilingual model challenges. The new NLP algorithms require massive amounts of text as input, and as we have noted before, most of the internet is written in English. Separate languages express the same content in fundamentally different ways. Agglutinative languages like Japanese and Finnish versus isolating languages structure their words in very different ways, and that has to be programmed for in the algorithms. There's also 4 large types of ambiguity that vary between different languages. That's lexical ambiguity, referential, scope, and structural ambiguity. These types of ambiguities happen in English as well, but happens more commonly and more complexly when you account for a multitude of languages in a multilingual model instead of monolingual. So it's important to still address the types of ambiguities that can arise. The first one being lexical ambiguity, when a sentence contains a word that has more than one meaning. Example is a driver, the driver of the car, or a type of golf club, and a bank, a river bank, or a financial institution. The words that are lexically ambiguous vary with the language, so it can be especially hard to figure out what words translate to what when one word can mean several different things. Referential ambiguity refers to when a sentence references an entity that was possibly mentioned in a previous sentence or sentences before that. An example is Steve and Bob just met today. They went to the park and had fun. You can assume they is referring to Steve and Bob, but they could be referring to something 2 sentences ago. Scope ambiguity is syntactically unambiguous, but semantically ambiguous. Scope ambiguity occurs when a word that expresses quantity fails to address what is quantified. An example is 2 students met with every teacher. You can interpret that as, did 2 unique students meet with every single teacher? Or did every teacher meet with 2 students, but different students may have met with those different teachers? And lastly, structural ambiguity, when a context-free grammar may assign 2 or more phrase structures, parse trees, to one in the same sequence of terminal symbols, word-to-word classes. In other words, due to different syntactic structures associated with the same sequence of words, we have an ambiguity in the actual meaning of the sentence. An example is Jessie called her boyfriend from Europe. Although the sentence is correct, we technically don't know if Jessie was in Europe when she made a call to her boyfriend, or was Jessie's boyfriend in Europe when she called him. Another challenge that becomes exceptionally complex when dealing with the multilingual model is the stemming and lemmatization of a document. In a multilingual model, rather than using only the morphological rules of a single language, the rules of multiple languages are considered simultaneously and relative to each other. Where in stemming, you usually take a crude approach of chopping off the ends of words. In lemmatization, you do things properly, usually with a morphological analysis using one of the 3 morphological approaches of morpheme-based morphology, lexeme-based morphology, or word-based morphology. Also, when it comes to multilingual models, lemmatization usually requires a neural network for learning, which we will get into later. Another reason morphology analysis is complex in multilingual NLP models is that English morphology is relatively basic, and as a result, advancements in morphological analysis has not been focused on effective translation for complex morphological languages. A solution to this has been cross-lingual learning for low-resource languages. In unsupervised cross-lingual representation learning can be seen here as an instance of transfer learning. It's important to note that transfer learning is particularly only useful when the 2 languages share some sort of base level structure. When the 2 languages are a lot more complex and differ from each other in the ground level structure, then we apply different types of machine learning concepts. And lastly, I'd like to consider the interesting challenge that different cultures have words related to that culture's ideas or objects, and sometimes have no translation in another language, like Yukado, which is a specific type of woodblock Japanese art, has no translation in other languages, or a kimono, which is a traditional Japanese dress. Now, moving on to the good stuff, some of the solutions that have caused NLP to be revolutionized recently is the advancements in deep learning and the advancements made by, I would seem to attribute to Google's BERT model, specifically the transformer in it that we will cover soon. Popular models today include Laser, which is a zero-shot transfer-based model made by Facebook, which essentially creates a vector representation of sentences that are generic with respect to the input language and task. Essentially, Laser maps sentences in a highly dimensional space in the hope that the same statement in different languages will be neighbors in the semantic vector space. Next is MBERT, which is the multilingual adaptation of BERT made by Google, which we will cover in more detail in the coming slide. I should mention now that MBERT is a multilingual version of BERT that is trained on 104 languages and is one of the main reasons there has been so many advancements in multilingual models today. Next is XLM and XLMR. XLMR is just the same as XLM basically, but it's at scale. It uses more languages and more data. And XLM can be seen as an enhanced BERT by basically it expands upon BERT's transformer architecture and uses self-supervised training. XLM and XLMR are both made by Facebook. Also, as we will see in the upcoming slide, all these modern models use mass language modeling, which is a deep learning technique. Here we take a look at what mass language modeling is and why it's so prevalent in modern natural language processing models. Mass language modeling is a self-supervised pre-training objective. It's widely used in NLP for learning text representations. It's especially important technique in transformer architecture, as mentioned previously, was created with BERT. Trained model learns to predict the missing token, essentially reconstructing the non-masked input, which you can see in the picture to the right, where boring is masked, and the transformer encoder trains to predict that word and reconstruct the sentence. And the principal objective is that predicting the masked words with the help of the surrounding text helps learn potent contextualized representations. Essentially, by doing this a bunch of times, the program will learn patterns for whatever language it's given. So then, the MLM trains a model that predicts a random sample of tokens from the input, which have been replaced by a masked placeholder in a multi-class environment across the entire vocabulary. BERT is Google's groundbreaking bidirectional encoder representation from transformer. As you can see to the left, that is an overview of a transformer, and BERT takes that architecture. It actually founded that architecture and causes some groundbreaking advancements in natural language processing. BERT was trained on a monolingual corpus for initial training, specifically English, but later 104 more languages were introduced to fine-tune BERT into what is known as MBERT or multilingual BERT. The multilingual BERT was trained on Wikipedia with shared vocabulary in multiple languages, and large languages were undersampled, while smaller languages were oversampled to account for the disparity in sample size. BERT is not a machine translation model, but rather an NLP tool to help extract meaning from words. Now, regarding the transformer consists of two key components which you can see on the left, known as the encoder and the decoder. The encoder, if you give the transformer, say, an English sentence and a Japanese sentence, the encoder takes the English words simultaneously and generates embedding for every word simultaneously. These embeddings are vectors that encapsulate the meaning of the word, so similar words have closer numbers. Then the decoder takes the embedding from the encoder and the previously generated words from the translated Japanese sentences, and then uses them to generate the next Japanese word. Then if you can keep generating the Japanese translation one word at a time until the end of the sentence is reached. This framework is appealing because we can see the separation of tasks. Specifically, we can see that the encoder learns language. It learns what English is, what is grammar, and what is context, while the decoder learns how English words relate to Japanese words. Stacking the encoder side of the transformer is actually what gives us BERT, which is in the name bidirectional encoder representations from transformer. Taking a slightly deeper look into the cross-lingual word embedding, you can see that words from multiple languages are embedded in the same vector space as mentioned previously. This allows the model to complete downstream tasks like text classification and clustering while also leveraging semantic information. The image below is a image from the Engineering at Meta blog, and this illustrates on the left side we see a monolingual embedding space, and on the right side illustrates this is specifically Laser's approach to multilingual word embedding using a single shared space, but this is a very similar approach to all the multilingual word embedding now. As if Google's BERT wasn't impressive enough, Facebook went on soon afterwards to expand upon it to create XLM Roberta, which is an expansive single large model for multilingual language processing. In the picture, you can see that just like BERT, we utilize marked language modeling, and that XLMR is pre-trained on 2.5 terabytes of filtered Common Crawl data containing 100 languages, which is significantly more expansive than BERT. XLMR, as a result, outperforms MBERT on cross-lingual classification by up to 23% accuracy on low-resource languages, and is considered cutting-edge technology for cross-lingual classification, question answering, and sequence labeling. More accurately, Roberta was pre-trained with the masked language modeling objective, and that becomes basically from a sentence, the model randomly masks 15% of the word in the input and then runs the entire masked sentence through the model and forces a prediction for the masked words. This differs from previously mentioned techniques like in BERT, where usually you see the next word one after the other in the prediction sequence. Using the method created by Facebook for Roberta, the model is able to learn the inner representations of 100 languages that can be used to extract features which are then very useful for downstream tasks. In closing, some applications of multilingual language processing and the models is that companies that are international can make use of it in their international queries and customer service forms, where the algorithms can better extract the meaning from different languages for global or international customers. This is also useful in detecting spam or hate speech in any language. This is specifically important for websites like Facebook or Twitter, where they are prominent around the globe and they need to filter out a lot of bad content in a lot of different languages. And finally, making a model for every language is very expensive, and doing it for every different type of task is very time consuming. This approach with XLMR is a big win for one model for many multilingual language processing modeling. This approach makes it easier to develop and release high-performing products in multiple languages simultaneously because companies are able to process the text on those websites simultaneously and with just their one model.